So we're going to just spend a bit of time looking at types of formulae that are commonly used in organic chemistry. This is obviously a fundamental thing that we need to get right because otherwise we're going to really struggle when we come to tackle more complicated questions. So the first one we look at is the general formula, and that's for the general formula for homologous series, for example the alkanes. And for any alkane, if you have n number of carbon atoms, you have double the number of hydrogens plus 2. And you can do that for most of the homologous series, and it's really useful for when you need to predict the formula. So for example, if you have 10 carbons, you know you're going to have 22 hydrogens. The next one are displayed formula. So they show all atoms and all bonds, and this is really important. It's one that people can lose marks on when they forget, for example, ethanol, they forget the OH bond there. It's very common for people to forget to put that one, and instead they do everything right, but then they just put OH like so. That's not right. You must show the OH bond. And you can see drawn there, it is a bit time consuming, but it does make it completely clear what the molecule looks like. So we now look at structural formulae. So these, as it says, give the minimum detail using conventional groups. So it just shows how the structure is arranged without going for the full displayed formula. So for propane, you can see it there. For ethanol, we have there, and for 3,3-dimethylpentane is shown there. As you can see, it's much faster to do those. You don't need to draw all the bonds, and it clearly indicates the structure of the compound. Any branches, as you can see for 3,3-dimethylpentane, which we've shown there, you can draw by putting them in brackets. So you can see here you've got your two CH3 groups there in a bracket, and that represents those two there. So just give you an idea how you draw them for the series that we've already come across, we're just going to go through those now. So first of all, for the alkenes, these were the ones that we saw in the last video. So to just draw them in using structure formulae, very similar. You don't need to put the carbon-carbon double bond in if you don't wish to. That's fine. And really, it doesn't make it a lot easier. You can just see there, if I highlight that group there, you can put your CH2 groups in brackets. So if you have a lot of CH2 groups, a long chain, you can put them all together and just in brackets like so. So looking now at the alcohols, again, very similar, just putting the OH group there. Aldehydes, the way we show the aldehyde group is CHO, and that's really important. You have to do it as CHO. You must be very careful that you don't put it as COH, because if you show it that way, that is actually an alcohol. So you mustn't show it that way. You must always show it as CHO, like so. And if we move on to carboxylic acids, we show the carboxylic acid group as structural as COOH. Try to avoid CO2H. It's better to put COOH, just makes it a little bit clearer. Nitrile is very similar. Generally, you can show the triple bond if you like, or you can just show it as a CN if you wish to. It doesn't really matter for that one. It's just quite nice to show it as a triple bond, so it's very clear, but you can show it as CN, like so. And obviously here, if you wish to, you could have grouped those CH2 groups up together. So let's have a look at how we show the other groups. Halogenoalkanes, quite straightforward, very similar to the alkanes. Let's have a look. Ketones, you just show them as CO in the middle. For amides, they're shown as CONH2, which we put there. That just makes it really clear that is an amide there. And for acyl halides, you show this group as COX. So if it was SCl, for example, it would be COCl. So probably the hardest one that people find are using skeletal formulae. And these are just showing the carbon chain without any hydrogens, and you also add in the functional groups. So for propane, propane is shown like that. So as soon as your pen, this touches a paper, so this part there is a CH3, that's a CH2, and that's a CH3 there. So for example, when you start drawing it, as soon as my pen touches the paper, that is CH3, CH2, CH3, like so. So you couldn't do methane using skeletal because it would just be a dot, like so. Okay, so carrying on, ethanol. Very similar, but we have OH, like so. We show the functional group. So that is CH3 there. If we just show that, that's CH3, that's CH2, and that is my alcohol group there. And then finally, 3,3-dimethyl pentane is shown here. So again, you've got your 5-carbon chain, which is here, going like so. And then you show on this carbon here, which is that carbon there, 2 other branches coming off, which are your methyl groups. So how do we show the functional groups that we've met using skeletal formulae? Okay, well here we go. So for alkenes, propene is just shown by a double bond like so, so 2 lines. Alcohols we've seen are shown by an OH, so that would be propanol there. We've got 3 carbons. Aldehydes are shown like so. We don't show that carbon with the CO, that just becomes a line there, that's that carbon there. But coming off it, you've got your double bond O and your H. You show the H there. And then carrying on, for carboxylic acids, we show that as like so. So very similar to aldehydes, but you have the OH there rather than the H, like so. And finally, for nitriles, again, you just show that as like so. You don't show this carbon attached to the nitrogen there. That is just shown by the end of the triple bond. You just show the nitrogen. So CH3 is there, CH2 there, CH2 there, and then that carbon there is there. So let's carry on and look at the other groups that we've met. Haloalkanes shown there, so chloropropane is shown there. With the Cl, we just show the functional groups. Ketones like so. Amines, as you can see, are like so. Amides are very similar to carboxylic acids. And finally, acyl halides are shown. So you don't show carbon atoms, you only show functional groups where necessary. So we'll finish off by these two. Empirical formula of a compound that shows the simplest whole number ratio of atoms present, and molecular formula shows the total number of atoms present. So for example, let's have a look at butane. Butane has the molecular formula of C4H10. That is the exact, in every butane molecule you have 4 carbons and 10 hydrogens, but the empirical formula is the simplest ratio between those. So rather than 4 to 10, you can actually have 2 to 5 like so. So this one is a molecular formula, and that is what we would call the empirical formula. So you may have done something similar to this in when you looked in your first module, but we are going to find the formula now of a hydrocarbon. And we know that the hydrocarbon has 82.76% carbon and 17.24% hydrogen in it. And we're going to find its empirical formula, first of all. So we can't compare percentages, so we're going to pretend that if we had 100 grams of this compound, 82.76 grams would be carbon and 17.42 grams would be hydrogen. And when we do that, we can therefore find the moles. So the moles of carbon, we divide there's 82.76 by 12, and for hydrogen by 1, because that's their molar masses. So that gives us 6.897 to 17.24. Now obviously that's a ratio, but we can't put that in a formula. So we divide by the smallest one, which is 6.897, and that gives us 1 to 2.5. You can't again have a formula of 1 to 2.5, so you may remember to remove that 2.5, we times both by 2, and that gives us 2 to 5. So if we times both sides by 2, So 1 times 2 and 2.4 times 2, that gives us a 2 there, and that gives us 5 there. And once we've done that, so our formula, empirical formula, is C2H5. So once we've got that, we can now work out its molecular formula, because they've given us the molar mass, which is 58. So if we add up 2 carbons and 5 hydrogens, we can see that that does not come to 58. So C2H5 comes to 29, the mass of the empirical formula, which is half what our molar mass is supposed to be, 58. So what we need to do is we need to times our empirical formula by 2. And if we do that, we will find this to be C4H10 as our molecular formula. So on the next couple of pages, I have given you some molecular formula, structural formula, skeletal formula, displayed formula, and empirical formula with blanks. And what I'd like you to do, if you can, is have a go at filling in those blanks. So that's on this page, and also you could download a PDF version of this worksheet by following the link that's appeared there. On the next one there. And when you're ready, carry on watching the video and I will go through the answers for you. So here are the answers to those types of formulae question. I've underlined in red the ones that you were given and completed the blank boxes. So you can hopefully see where, hopefully you've got them all right. For some, the molecular formula and the empirical formula will be exactly the same. Others, it will be different. So, for example, C5H10 can become CH2. For this one, it's important to actually get it right around the double bond. This is actually shown as the cis isomer with the hydrogens on the same side, but more of that later on the next video. You can see here that you've got your CH3 branching, which is shown there and there for your skeletal and displayed formula. And C6H14 can become C3H7 in the empirical formula. And again, we've got the acyl halide there with the skeletal and the displayed showing. And on the final page, you can see we've got the displayed for our amine there. And you've got your NH2 group coming off your carbon in the middle of the chain there, which is, of course, that carbon there. You've got your nice ketone there, propanone there. And finally, you've got your amide in your column there. So obviously we'll have lots more practice of those as we go through the coming modules, but hopefully that just makes it a little bit clearer as the types of formula you use. Again, probably structural is the best one to do if you can. Skeletal, really fast, but in my experience, if you don't use it too early, because it's really easy to miss out carbons, and therefore you'll lose marks. So just be really, really careful with that one.